In this video, we're going to talk about exponential functions and graphs. And then at the end, we're going to talk a little bit about exponential growth and some common problems that you might see in a pre-calculus or math analysis type class where you go over these kinds of things. So let's jump right into it. An exponential function looks like this. Here we have y equals 2 to the x and y equals e to the x. And they have these properties. All exponential functions have these properties where their domain goes from negative infinity to infinity. So it stretches all the way to the left and all the way to the right. As you can see pretty clearly by both of these functions, this one's going to travel all the way that way. This one's going to travel all the way that way, even though I didn't include the blue arrow there. This one's going to travel all the way to the right, and so is this one. The range is limited to 0 to infinity, so they're always going to be above the x-axis as long as they aren't reflected downwards or shifted downwards. As x approaches infinity, f of x also approaches infinity. That's the right-hand side of this function as it trends upward. It ticks upward in both of these examples. But as x approaches negative infinity, meaning as x goes to the left, f of x gets closer and closer to 0, which kind of goes hand in hand with this bottom point that there is a horizontal asymptote at y equals 0. So as these functions go to the left, here and here, they get closer and closer to the x-axis. I also want to point out that these functions are always increasing. As they travel to the right, f of x always goes up. So this was in the toolkit functions video that I made a while ago. If you want to go check it out, it's up on the channel now. So I won't go too much into how to shift and reflect these sorts of things, but what I will do is show you some common problems. And most of those problems have to do with exponential growth, whether it be with money or pools of bacteria or stuff like that. Most problems involving these functions and or graphs involve exponential growth. So let's look at a couple of these examples. Okay, so here we have our first example. And it says initially there are 100 cells of bacteria in a pond where they double every single day. So the first day there's 100, the second day there's 200, and so on and so forth. How long will it take to reach 50,000 cells? And I left this little note here that tells us to use functions of the form a, b to the x. And as we're going to see, a is going to be our initial number, because when x, or in this case, our variable for time, so we can call it t, x, whatever we use, when that is 0, a is going to be the number that we're left with, because b to the 0 is very clearly 1. So a times 1 will be a, and that's the number we start with. So in this situation, we know that we have 100 cells. So if we want to use a function of this form, we can write that as f of x equals 100 times bx. And like I said, 100 because that's how many we start with. And when t is equal to 0, or x in this case, and we use 100 because we start with 100 cells. And when t is equal to 0, this b to the 0 power will go to 1, which leaves us with just 100. And now we want to figure out how much do these bacteria increase every single day? Well, we're told that. We're told that they double every day. So for every day, we want to multiply this by 2. So this b value here is going to be 2. So we'll have f of t is equal to 100 times 2 to the t. And we want to figure out how long it'll take. So we want to find t where we have 50,000 cells. So we want to plug in 50,000 for our f of t and solve it for t. So we'll have 50,000 equals 100 times 2 to the t. But now we can divide both sides by 100. That'll give us 500 equals 2 to the t. And now we want to take the log base 2 to cancel out this base right here. So we'll have log 2 of 500 equals t. And if you're not entirely familiar with this logarithmic form right here, or how to get rid of numbers like this where we have a base and then a variable in the exponent, I'm about to make a video on that, on how to deal with variables and exponents. So it should be up on the channel soon if it's not already up. Okay, so we know this number, log base 2 of 500, is our t. I'll go ahead and use a calculator and write that up here. So t is about 8.96. So it would take about 9 whole days for us to reach 50,000 cells. And we can check that pretty easily. We can double 100 over and over again until we reach 50,000. I'll go ahead and put a chart of that right here so we can see that in action. Okay, so we have our chart over here, and as you can see, if we continuously double this 100 cells initially, by day 9 we'll end up with 51,200 cells, which is exactly what we showed right here. Okay, so let's move on to another example. Okay, so here we have our second example, which tells us the population of China was about 1.3 billion people in the year 2013, with a growth rate of 0.6%. And we're asked to find China's population in 2022, which is the year I'm recording this video. Okay, but how do we want to do that? Well, first, let's go ahead and set up our function in the form of an exponential function. So we'll write it as ab to the x. And we'll make a our 1.39 billion people, because that's how many we start with. We'll assume our starting year is 2013. So we'll write f of x equals 1.39, and we'll write it in billions, so we'll just keep 1.39 as our number here, and this is times b to the x. Now this is a little bit different from our problem before, where we doubled every time period, whereas this time we're only increasing by 0.6%. So instead of 2 here, we only want to increase it by a little amount. So how do we write that? Well, we're going to increase, so we need to be at least 1, because if we multiply by any number less than 1, then we're just decreasing the number. So it's going to be 1 plus this 0.6%, so we're going to write that as 0.006, like that. We write it like this because generally we write percents as decimal numbers. This 0.006 represents our growth rate. This is the decimal representation of this percentage. And this is all to the x power. So this whole thing is our b right here. And this is our function f of x, like that. Now that we have our function, all we're asked to do in this problem is plug in the year 2022. But since our starting year was 2013, we just need to find the difference between these years, and that's 9. So we'll plug 9 in for x here and see what we get. So let's go ahead and do that. We have f of 9 equals 1.39 times 1.006 to the 9th. And so f to the 9 is equal to 1.467 about. So I just did that by plugging this into a calculator really quick. And so this is our final answer to this problem. China has approximately 1.467 billion people in 2022, according to this growth rate. Okay, let's move on to one last example. Okay, so this will be the last example we do for exponential functions, and we're going to slightly tweak this after we do this version of it to a slightly different version, and then we'll end the video off. So this problem says that if we invest $3,000 paying 3% interest compounded quarterly, how much will the account be worth in 10 years? And I've written this compound interest formula on the board right here that I'm going to go ahead and box in orange, which tells us exactly what we need to do. We write a as a function of t, and p is our principal, or our initial value of the account. So that's 3,000 that we'll plug in there. And then r is our interest rate. So that's 1 plus 0.03, changing this percentage to a decimal. And then n is the number of times per year that it's compounded. So that's 4 because we're compounding it quarterly. And then n again is 4, so we have 4t up there. Okay, that's great. Now we want to know how much the account will be worth in 10 years. So all we have to do is plug in 4 for t. So let's go ahead and do that. That's going to give us a to the 10. A of 10 equals 3,000 times 1 plus 0.03 divided by 4 to the 40th power. And you can go ahead and plug this into a calculator. This is going to give us about $4,045.05. So this is how you do this kind of problem. You just plug in your principal for P, your interest rate for R, the number of times you're compounding this quarterly for N, and N up here, and then the amount of time in for T. And you can solve for other variables. You might have questions that ask you to solve for the rate given your initial value and your current value at the time. For instance, it might give you this 40.45 with 5 cents and 10 years, along with this $3,000 principal and compounded quarterly, and ask you to find the interest rate. You might have to solve for any of the variables in this equation. This time we just had to solve for a of 10. Okay, so now that we're done with this problem, let's slightly tweak it to a very similar problem that has a similar formula to this one. Okay, so I've changed the problem slightly. So now instead of having compounded quarterly interest, we have compounded continuous interest. And that gives us this formula P times e to the RT. And we use this number e, this is a number, not a variable, to signify continuous growth, or continuous compoundedness in this case, of our bank account. You could have continuous growth of bacteria or continuous growth of population, as we've seen in our other examples. And that'll just replace your b in those examples. Where we had a b to the x, now we have an e to the RT. And this just signifies the continuousness of it. And we'll get into the reasons we use this number e and why it's so special in a later video. Okay, so let's go ahead and jump into this problem. We have $3,000 principal, that's not going to change. So we have a to the t equals 3,000 times e to the r, that's our interest rate, so 0.03 t. And we use e, like I said, because we have compound continuous interest here. Okay, but now we just plug in 10 for t, and that gives us 3,000 e to the 0.3. And so you can plug this into your calculator and see that after 10 years, the account will hold about $4,049.58. Before we finish this video off, I just wrote down a few notes about E that I think are pretty important and need to be shared on a video that accompanies exponential functions. So E is defined as this number, 1 plus 1 over n, all to the nth power as n goes to infinity. And that's very important for continuous functions because, as we saw before, where we had 1 plus a rate inside, that's this number here, but as it increases to infinity. And E is about 2.718282, and then it continues on forever and ever because E is an irrational number. And it's used for many real-world growth rate problems, like the ones that we've looked at here. And it was named for Leonard Euler, who first discovered E and many of its properties and uses. That's enough for now.